here we have to evaluate line integral. So I'm gonna start out with the formula. That ds is the arc length formula that you learned from Calculus 2 or from high school Calculus BC AP. So I'm going to restate that. Like that. Okay, now we have the formula. We have to plug it in the right values from the given direction. So we know t goes from 0 to 1, and we have the function, and we have dx over dt that can be calculated from our parametric equation. So I'm gonna find dx over dt and then dy over dt. Dx over dt is simply 2t, and dy over dt is simply 2. Now we just have to plug it in. So this part will go here, and these will substitute accordingly. And our time, the upper limit is 1, lower limit is 0. Okay, here's something we have to be careful. It said the xt and yt, so let me plug t squared into our x and then 2t, and you will notice that they multiply out to 2t cubed. Okay, now we are complete. And besides, we have a dt, so we have to make all the terms inside the integral between integral sign and the dt should be in terms of dt, in terms of t. Yeah. So let me erase something. So I can move out that 2 outside of our integral because it's a constant. Okay, I will simplify further. I can pull out that 4 outside by factoring, and when you take out the radical 4, you get 2, and I can multiply that 2 to the existing 2 in front of the integral sign, so I should get 4 in front, and we get up to here. Now you might wonder, how should we solve this? Looking at this, you might say u substitution might not work, because if you set this equal to u, then how do you take care of t cubed? Well, actually, u substitution definitely works. Let me show you why. If I set that u equal t squared plus 1, and then, so that's gonna, under the radical we'll have u, and we can rearrange it. Okay, actually, before we do that, let me demonstrate that by breaking this apart. I'm gonna put that t, 1t toward the dt, so that you will see you will see that by taking the derivative of u, that we can take care of that t dt. So if I derive u here, I get du equals 2t dt. 1 is a constant, so it goes away. And I have t dt, right? That means I can simply divide it both sides by 2 and then cancel out 2. So I have t dt. I can simply substitute du over 2 and replace t dt. And you might say, what about t squared? You have u equals t squared plus 1. We can just simply subtract 1, then you get u minus 1 equals t squared. Then we can substitute everything in terms of u. And don't forget to change our upper limit and lower limit. Upper limit was 1, so t equals 1. So to find u, you just have to substitute here. So u of 1 in terms of t becomes 2. U of lower limit 0 becomes 1. So if I rewrite this now, we still have 4 in front, and then our upper limit changes to 2 and lower limit changes to 1. T squared happens to be u minus 1. And then under the radical we have simply u, and t dt became du over 2. That 1/2 can multiply with 4 in front, so you get 2 integral. At this point, you can substitute u's. U to the 3 over 2 and u to the 1/2. Okay, we just use a simple antiderivative rule by adding 1 to our exponent, and don't forget to divide those exponents. Then you substitute u. You know that's u, plug it in, you get 2 times 4 times radical 2, and plug it in again to our second term, and you get 2 times radical 2 minus now you plug in our lower limit, u1 equals 1, so simply 2 over 5th minus 2 over 3. Okay, we can have a common denominator as 15. Then to get 15, I have to multiply both top and bottom by 3. Here I have to multiply by 5. Here 3, and here 5. Okay, 6 times 4, 24 radical 2. 10, 20, 20 times radical 2. 6. Okay, don't forget to have plus 10, because notice that minus. Notice that minus here will cancel out, so I have a plus 10. Okay, so I have a 4 radical 2 plus 4. I can pull out that 4 out, or factor out 4. I get 2 times 4, 8. Okay. And I have 15 on the bottom. That's our final answer.